All right, so where are we today? 16.2, part 2. Transforms of derivatives. And in a few lessons, we will also talk about derivatives of transforms. So we kind of do it both ways. So we're going to start, we're going to suppose that we have f prime, up to the n minus first derivative, and these are continuous. On 0 to infinity. So we have nice functions here. And the nth derivative is piecewise continuous. On that same interval, 0 to infinity. And our f prime up to f, the nth derivative, are of exponential order. Because we want to be able to take Laplace transforms. And I'm going to say, just to be explicit, for which we have our C is specified by absolute value of that nth derivative is less than me to the ct. So just our definition of exponential order. Then for s greater than c, we have the Laplace transform of our nth derivative is s to the n, the Laplace transform of our function, minus s to the n minus 1 times our function evaluated at 0 minus s to the n minus 2 times the derivative of our function evaluated at 0 minus minus the n minus first derivative evaluated at 0. Where f sub s is the Laplace transform of f. So when we take the derivative, we take the transform of a derivative, we end up with an algebraic function, because s, the n, these are just exponents, these are our coefficients in an algebraic expression involving the Laplace transform of our function. And let's think for a second about why we end up with these f of 0, f prime of 0. If we think about our definition of the Laplace transform, we're integrating some function from 0 to infinity. So we're going to evaluate these things at 0. So I'll show why this works. It's not complicated to understand why this is the case. But I want to point out here. So what we end up doing here is we have a differential equation. We're going to apply the linearity principle and take the Laplace transform of all of our various derivatives. and the Laplace transform of the right-hand side of our differential equation, which is usually some function of t. And then we just end up with an algebraic equation where we can solve for the Laplace transform and then apply the inverse transform to get our solution for an initial value problem. Because we need to know f of 0 and f prime of 0. So that's kind of a nice thing. All right, so let's take a look at why this is the case. So I'm going to say something that you'll often see if you go further in math, if you do proofs of various things, without loss of generality. So W-L-O-G. Without loss of generality, we're going to assume F has a single point of discontinuity. And we're going to say that's at t equals t0. If we have more than one point of discontinuity, then we just, when we apply our Laplace transform, we just have more integrals that we have to add together. So the Laplace transform of f prime of t, by the definition, is going to be the integral from 0 to t0 of e to the minus st f prime of t dt plus the integral from t0 to infinity of e to the minus st f prime of t dt. And we're going to integrate by parts. So I'm going to go over here and I'm going to say integration by parts. We're going to let u equal e to the minus st. When we've done the definition of the Laplace transform, we see this integral come up a lot when we integrate by parts. Du is minus s e to the minus st. dv is f prime of t, and so v is just going to be f of t. When we integrate f prime, we just get f. So this is going to equal, for the first integral, we get u times v, so we get e to the minus st f of t, and we're evaluating that on 0 to t0, minus integral of v du, so that's going to be minus negative, so we get a plus. So I'm going to say plus the integral from 0 to t0 of s e to the minus st times f of t dt. That's for our first integral. Plus, we're going to write it down here, plus, when we integrate this by parts, we get e to the minus st f of t, and we're evaluating that on t0 to infinity, and we get a plus, a minus, negative, plus integral from t0 to infinity of s e to the minus st f of t dt. So this is our first integral here. This is our second integral here. Well, when we evaluate this at our limits, we get e to the minus s t0 f of t0 minus, when I evaluate this at 0, this gives me a 1 here, and I get f of 0. There's that f of 0. And I get a plus this integral from 0 to t0. I'm going to set that here at the end. So we get a plus, and I'm going to get an s integral from 0 to t0 e to the minus st f of t dt. So this one's going here. And then we have a plus. When we evaluate this, we have the limit as t approaches infinity of e to the minus st f of t minus, when we evaluate this at t0, minus e to the minus st0 f of t0. And then I get a plus s integral from t0 to infinity of e to the minus st f of t dt. Well, we see that these two terms, we have a positive one here and a negative one there, so those add to 0. We have a negative f of 0. This limit, because f is of exponential order, and if we assume that s is positive here, this limit is 0. And then here we have plus s times the integral from 0 to t0, e to the minus st f of t dt, plus integral from t0 to infinity of e to the minus st f of t dt. Well, this term, this quantity, is the Laplace transform of f of t. We have one point of discontinuity at t0. So that term is the Laplace transform of f of t. So we get minus f of 0 plus s Laplace transform of f of t. And we could write L at prime of t equals s f of s here minus f of 0. So it's just a straightforward application of the definition of the Laplace transform and integration by parts. And then to get our higher order derivatives, we just apply this recursively. So in other words, for a second derivative, the Laplace transform of f double prime of t is going to be s times the Laplace transform of f prime of t minus f prime of 0. Here our function now is f prime, and we're taking the derivative of f prime. And this part we would substitute. Which we got here. So we get s times this whole thing. S f of s minus f of 0 minus f prime of 0. And we get s squared f of s minus s f of 0 minus f prime of 0 for our second, the transform of our second derivative. And we could continue to do that for the third and fourth derivative. So now we have a way to take the Laplace transform of derivatives. right, questions? So now let's talk about solving. Linear ordinary differential equations. We can apply the transform to linear initial value problems where our differential equation has constant coefficients, because we don't really know how to take derivatives of products yet. Or sorry, Laplace transform of products. So our differential equation is a linear combination of the derivatives of our function. So we're going to be given a sub n by n minus 1 plus a sub n minus 1. It's been a while since we've written this one. Sorry, this should be y n. And here we have our n minus first derivative. Plus dot 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 plus a0 y equals some g of t. And we have y of 0 equals y0, y prime of 0 equals y1, and n minus first derivative evaluated at 0 is y n minus 1. Apply the Laplace transform. And we know we can apply, if we are applying it to this entire thing, we can apply it term by term by the linearity principle. We get a sub n Laplace transform of the nth derivative of y plus a sub n minus 1 Laplace transform of the n minus first derivative plus a0 Laplace transform of just the function, and that equals the Laplace transform of g of t. And we know that the Laplace transform of our derivatives all end up just with our term that has a just the Laplace transform of our function. And this becomes a sub n. We end up with s to the n y of s minus s to the n minus 1 y of 0 plus up to the n minus first derivative evaluated at 0 plus a sub n minus 1 times s to the n minus 1 y of s minus, this should be a minus here, and this should be a minus, we're subtracting, minus s to the n minus 2 y of 0 minus dot 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 minus yn minus 2 at 0 plus, and we get a sub 0 y of s equals g of s, which is an algebraic equation in y of s. So we solve for the Laplace transform of y. We might need to do some algebra. Usually need to do some algebra. Once we get the transform, usually this part is easy, solving for y of s. Then we need to transform what we end up with, do some algebra to what we end up with to apply the inverse transform. And then So there's some steps in between here. Apply the inverse transform. To get the solution. And the nice thing we will see is that we can apply the Laplace transform for these functions here on the right-hand side to make our equation non-homogeneous. We can apply the Laplace transform, and we'll see that as we move forward, to different kinds of functions that will make it possible to use the Laplace transform when other methods will not work so well. One of those types of functions will be piecewise functions. We can have a driving function that's a piecewise function. Something's happening for between t equals 0 and some time, and something else is happening after that. Okay, so let's look. I just want to go through one example. We want to solve y double prime minus 4y prime equals 6e to the 3t minus 3e to the minus t. Y of 0 equals 1, and y prime of 0 equals negative 1. These are especially nice when our initial conditions are that both of these things equal 0, because then we have many less terms. If we were not using the Laplace transform here, what method would we choose to solve this? We could use undetermined coefficients on this part. But on this part, could we use undetermined coefficients? Yeah, I think we can. We could use undetermined coefficients here. Undetermined coefficients on these exponential functions, that wouldn't be too bad, would it?
This is doing like the
A e to the 3t.
Yeah.
Unless
you'd have m squared minus like 4m that's right?
So that's for the complementary solution.
Yeah.
So unless the complementary solution contained some of these, then we'd have to make some adjustments. So this is not a terrible equation to solve. Maybe not a terrible equation to solve using methods that we already know. Well, let's look at using the Laplace transform. So we'll say the Laplace transform y double prime minus 4 Laplace transform of y prime equals 6 Laplace transform of e to the 3t minus 3 Laplace transform e to the minus t. The Laplace transform of y double prime is s squared y of s, where y is the Laplace, capital Y is the Laplace transform of this, minus s y of 0 minus y prime of 0 minus 4 Laplace transform of y prime is s y of s minus y of 0, and that's going to equal 6, the Laplace transform of e to the 3t, 1 over s minus 3, minus 3, the Laplace transform of e to the minus t is 1 over s plus 1. So I'm going to gather my terms that have a y of s. So I get s squared minus 4s here times y of s. I'll gather the y of 0 terms. So we get plus negative s plus 4 y of 0 minus y prime of 0 equals all this stuff. 6, 1 over s minus 3, minus 3, 1 over s plus 1. Well, this is negative s plus 4, y0 is negative 1. So what do we end up with? S squared minus 4s, y of s, and y prime of 0 is negative 1. So I think we get a negative s plus 5. This is 1, so we get a negative s. Here we get a 4 plus 1. So negative s plus 5 equals 6 over s minus 3 minus 3 over s plus 1. I'm going to add all of this, or add s, subtract 5, so I get s squared minus 4s, y of s equals 6 over s minus 3 over s plus 1 plus s minus 5. Isolate y of s. So we get y of s equals 6 over s squared minus 4s, s minus 3, minus 3, s squared minus 4s, s plus 1, plus s minus 5 over s squared minus 4s. And I would factor this. I'm going to factor this to s times s minus 4, and this is s times s minus 4. So we have, and this would be s times s minus 4 also. So we have 3 sets there of nice partial fractions that we end up doing here. That's why I say use a calculator, use some online tools to help you with that. These are not terrible partial fractions, but there are 3 of them. And each of these has 3 terms. This just has 2, so that's not as bad. So I'm going to say partial fractions. We're thankful for technology. And we get y of s equals 5 halves times 1 over s minus 2 over s minus 3 minus 3/5 times 1 over s plus 1 plus 11/10 times 1 over s minus 4. And then we apply our inverse transform term by term. And we get y of t. Inverse transform of 1 over s is just 1. So we get 5 halves. Inverse transform of 1 over s minus 3 is e to the 3t. So we get minus 2 e to the 3t. Inverse transform of 1 over s plus 1 is e to the minus t. And the inverse transform of 1 over s minus 4 is e to the 4t. And there's our solution. Now, there is algebra involved here. If we had to do the partial fractions by hand, there's a lot of algebra involved. However, we don't have to worry about those cases with the undetermined coefficients. We don't have to worry if these are repeats of the solution in the complementary solution. We don't have to worry about the process of doing variation of parameters. And we also don't have to worry about the extra steps involved in solving for the constants, because this is an initial value problem. So our constants in our complementary solution come out automatically from using the Laplace transform. So there's a trade-off there. However, we will be able to apply the Laplace transform to differential equations we would not be able to solve in other situations. And we'll see those as we move forward. Yes?
Can we solve it without those initial conditions? Or is
Now with the Laplace transform, because the Laplace transform in the derivative has the y0, y prime of 0, you would have those as those would appear as unknowns in our as just some quantity in our solution.
Okay.
So could you do it with those as constants? I think maybe.
But we won't.
Yeah, we'll always use these for an initial value problem. All right, questions?
This is better.
Okay.
Because once you get then you get here. This gives you the something goes wrong. Something. Yes, they are. That's the layer.
There we go.
I feel like on the test I'm just gonna forget how to do partial
Yeah, that seems so far away now, doesn't it?
I know, it's supposed to be forever ago. I don't even remember what it was. That's like separation of whatever. Yeah, like divide into yeah.
Yeah, that we did separable. That's where he used the integrating factor.
I forgot that. We get our non-molar notes.
We did the exact equations, which were like what we did when we found potential functions, where we integrate the components and find the missing pieces. We did the homogeneous there. Yeah, homogeneous is pretty easy.
Yeah, that's. I feel like it's. That's nice.
No, I'm homogeneous.